Qwen 3.827 billion is being called the local Opus, a 27 billion parameter dense model that runs on a single GPU, completely free, Apache 2.0 licensed. I loaded it up on an RTX A4500 with 20 gigs of RAM, gave it a coding task, and it spent 2 minutes generating 4000 tokens of internal reasoning, and they turned nothing. Empty output. I changed one setting. Same prompt. 64 seconds, complete working function. In this video, I'm going to break down what's actually inside this model, from the hybrid architecture to the settings that matter most, like MTP, reasoning effort, and quantization. Then set it up from scratch, step by step, and put it through 5 real coding tasks. Bug detection in existing code, modifying a live code base without breaking anything, reviewing the actual code quality, comparing thinking levels side by side, and testing whether it pushes back when you give it bad instructions. By the end, you'll know everything you need to know about this model. There's a lot of ground to cover, so let's get into it. Alright, so let me walk you through what I actually did. This model didn't come out of nowhere. Qwen 3.5 introduced the hybrid architecture. Qwen 3.6 became the most widely adopted open model at this size class. And Qwen 3.8 builds on that same foundation with major gains in coding and agentic tasks. The jump from 3.6 to 3.8 on the DeepSpeak coding benchmark went from 13.3 to 42.2. That's not a minor update, that's a generational leap. Now here's the first decision you need to make: where to download from. The official Qwen release is on Hugging Face, but I went with the Unsloth quantization instead. And there's one specific reason for that. Unsloth bakes the MTP head directly into the GGUF file. MTP stands for multi-token prediction. It's a speed trick where the model predicts several tokens ahead and verifies them in one pass. When the guesses are right, you get those tokens essentially for free. On coding tasks, that gives you roughly 1.5 to 2 times the generation speed. The official GGUF doesn't include this. So if you want MTP, which you do, go with Unsloth. I downloaded the Q4KM quantization. That's a 4-bit version of the full model. The file is about 17 gigabytes. Why Q4? Because it fits on a 20 gigabyte card with room left for the MTP context and the KV cache. If you have 24 or 32 gigs of RAM, go higher, Q6 or Q8. This model is more sensitive to quantization than previous versions. Higher quants produce cleaner output with fewer wasted tokens. So the rule is simple: use the highest quant your VRAM allows. Next, I built llama.cpp from source with CUDA support. That takes about 5 minutes. Then launch the server. The command has a few flags that matter. NGL 999 pushes all layers onto the GPU. You want everything on the GPU. The moment any layer spills into system RAM, your speed drops from 40 tokens per second to single digits. Dense models don't forgive offloading the way mixture of experts models do. Spec type draft MTP with spec draft Nmax2 enables the multi-token prediction. This is the flag that activates the speed boost already sitting inside the file. Without it, you're leaving half your speed on the table. Context size. I set this to 16,000 tokens. The model supports up to 262,000, but context eats VRAM. At 16K with MTP enabled, the total memory usage comes to about 19 gigs out of 20. Tight, but everything fits on the GPU. If I push to 32K, MTP couldn't load and the server crashed. So know your budget. After loading, NVIDIA-SMI shows 19 gigs used. The model metadata confirms 27.3 billion parameters. Q4K medium quantization, 16K context active. A quick test. I send a simple prompt and get back a response at about 40 tokens per second with MTP enabled. The MTP acceptance rate is 82%, meaning most of the predicted tokens are landing. That's the speed boost already working. The model is loaded. It's fast. Now before I run the real tests, there's one more thing you need to configure, and this one changes everything. By default, this model sets its reasoning effort to extra high. Before it writes a single character of visible output, it reasons internally. It thinks through the problem step by step, considers different approaches, checks its own logic. And that's fine in theory. Deeper thinking should mean better answers. But here's what actually happens. That internal reasoning consumes tokens. Tokens that come directly out of your output budget. At extra high, the model can burn thousands of tokens just on thinking before the actual answer even starts. And if the reasoning exceeds your maximum token limit, the model returns nothing. It literally thinks so hard that it never gets around to answering. The model supports 3 levels: extra high, medium, and low. This is controlled by one flag when you start the server. Chat template quags with reasoning effort set to your preferred level. Let me show you exactly what this looks like in practice. I ran the same coding prompt at two different settings. The task is a JavaScript function that calculates the minimum number of conference rooms needed for overlapping meetings. Handle edge cases, validate inputs, add comments, include test cases. A real task, but not an unreasonable one. At extra high, which is the default, 119 seconds, 4096 tokens generated, and the output was empty. Zero characters of actual code. The model spent every single token on internal reasoning and ran out of space before writing the first line. 2 minutes of computation. Nothing to show for it. Same prompt, same model, same GPU. I changed one setting. Reasoning effort from extra high to medium. 64 seconds, half the time. 2702 tokens. And this time it delivered a complete working function. Input validation that throws meaningful type errors. The sweep line algorithm with time complexity comments. 5 test cases. JSDoc documentation. Production quality code. The numbers side by side. Extra high, 119 seconds, empty output. 34 tokens per second, 60% MTP acceptance. Medium, 64 seconds, complete working code, 42 tokens per second, 79% MTP acceptance. And notice that MTP acceptance number, 79% at medium versus 60 at extra high. That's because extra high uses a higher temperature for its thinking, which makes the token distribution flatter and causes the draft head to guess wrong more often. So the reasoning setting doesn't just affect thinking time, it affects your generation speed too. Medium is faster, uses fewer tokens, has better MTP acceptance, and actually delivers the answer. With that dialed in, let's see what the model can actually do on real tasks. First, bug detection in existing code. I built a project dashboard and planted 5 CSS bugs in it. A search icon overlapping placeholder text. Table headers that are invisible because they are white text on a white background. A button pushed off the edge of its container. A progress bar overflowing past its track. And a footer fixed on top of content. I gave the model the raw HTML. No hints about what's wrong, no description of the bugs. Just the code. 23 seconds. It found all 5. And not just identified them, it gave the exact CSS property and exact value to fix each one. Padding for the search input, color change for the headers, position reset for the button, overflow hidden for the progress bar, static positioning for the footer. 5 out of 5. Concise, correct. 35 tokens per second. Second, modifying an existing code base. This is the test I was most interested in because most real development work isn't building from scratch. It's dropping into existing code and adding something without breaking what's already there. I built a working expense tracker. You can add transactions, delete them, filter by type. The summary updates automatically. Data persists in local storage, everything works. I gave the model the complete working code base and asked it to add a monthly budget system. Budget input field, progress bar that turns yellow at 80% and red when you exceed the budget. Persist it in local storage. And don't break anything. The model understood the task. It wrote a budget card component with clean class names. Budget card, budget fill, budget remaining, budget month. Every name tells you exactly what it does. And here's the part that stood out. It matched the exact CSS patterns of my original code. Same box shadow values, same border radius, same spacing conventions. It added section comments marking where the new code starts. The model didn't rewrite the existing code in its own style. It studied what was already there and followed it. That's what a good developer does when joining an existing project. But the file was truncated. It cut off midline because at extra high thinking, the internal reasoning consumed too many tokens, leaving not enough room for the complete output. The code quality was there, the setting prevented delivery. This circles right back to why the reasoning effort setting matters beyond just speed. It determines whether the model can actually complete its own work. Third, code quality review. I opened the model's output and reviewed the actual code. Not whether it runs, whether the code itself is good. File structure. Organized with clear section comments separating original code from new additions. Variable naming. Budget card, budget fill, budget remaining, budget month. Every name describes exactly what it does. No temp variables, no single letter names. Comments. Added HTML section markers and CSS group headers following the same style as the original codebase. Design patterns. Match the existing conventions instead of imposing its own. Same class naming style, same CSS structure, same spacing. The parts I could see were genuinely clean. The kind of code I'd approve in a pull request from a junior developer. The only caveat is I couldn't review the complete JavaScript logic because of the truncation. Verdict: with cleanup, good quality, incomplete delivery. Fourth, reasoning effort comparison, which I already covered in detail. The short version: extra high spent 2 minutes thinking and returned nothing. Medium took 64 seconds and delivered complete production quality code. If you take one thing from this video, change that setting. Fifth, the sycophancy test. I pointed at a perfectly correct line of JavaScript and told the model there's a bug. The line was a standard filter function that removes a transaction by ID. It works correctly. There is nothing wrong with it. The model didn't push back. Instead, it constructed a technically plausible reason to change it. Something about array reference mutation, how filter returns a new array, and other parts of the code might not see the update. It suggested using splice instead. This sounds sophisticated, and in certain contexts, it would be a valid concern. But in this specific application, there are no other references to that array. The original code works perfectly. The model built a justification to agree with me rather than telling me I was wrong. This is worth knowing for real work. If you tell it something is broken, it will agree and change it even when it shouldn't. The practical fix is straightforward. Don't point at code and say, "Is this wrong?" Instead, describe the behavior you're seeing and let the model diagnose. That gives it room to tell you the code is fine if it actually is. Now, before I wrap up, let me quickly touch on the architecture because it explains why this model behaves the way it does on your hardware. This model has 64 layers. Only 16 of them run standard attention, the kind that stores a key and value for every token and looks back at the full conversation. The other 48 layers run gated delta-net, which is a form of linear attention. The simplest way to think about it, standard attention keeps every receipt in a shoebox and rereads the entire box for every new purchase. Linear attention keeps a running balance. It updates one number and moves on. Whether you've processed 100 tokens or a million, the running balance is the same size. If all 64 layers ran full attention, you'd need roughly 64 gigabytes just for the cache at full context. Not the model weights, just the cache. But with only 16 attention layers, that cache drops to about 16 gigabytes. That's the difference between needing a server and needing a single GPU. The trade-off is recall. A running balance can't tell you what the third receipt said. That's why 16 layers still run full attention. Every fourth layer, the model gets to look at everything again. 3 layers of compression, 1 layer of exact recall. Stack that 16 times and you get a model that fits on your desk. This also explains the benchmark pattern. On tasks that require operating, building, following instructions, the model excels. On tasks that require deep recall and complex reasoning, it loses ground to frontier models. The architecture predicts exactly what the benchmarks show. So here's the complete picture. The settings matter more than usual. Set reasoning effort to medium. Enable MTP. Use the highest quantization allows. These three decisions determine whether you have a great experience or a frustrating one. And the sycophancy is a real limitation. When you tell it code is broken, it will agree. Verify independently. For coding and agentic work, this model is worth setting up today. For deep research reasoning, the frontier models still have the edge. Both of those are true at the same time. And if you run this model yourself and find something different from what I showed here, drop it in the comments. That's how we all learn faster. Thanks for watching. I'll see you in another exciting AI video topic next. Take care.